So today I'm going to give a presentation that's based around 4 papers that our group have written in the last couple of years to try and show, I don't know, a flavour or a theme of our publications within our group. So the first publication is an annual reviews paper. We published this a couple of years ago. It was from myself and Bob Kopp and then our research group. We wanted to write this review paper because we wanted to try and look at the mechanisms that are responsible for sea level changes in the present and the past, and then look at their probabilities of these processes influencing sea level in the future. The other reason that we wanted to write this review is, as Adam said, I'm involved with the IPCC. So myself and Bob are heavily involved with the Chapter 9 on sea level, and we wanted to use this paper as a structural framework for writing the IPCC chapter. So sea level is far from a planar surface. It varies in time and in space because of a variety of different mechanisms. At the global scale, we have 2 dominant mechanisms. That's a change in mass or a change in volume. If you increase ocean temperatures, the oceans occupy greater volume and sea level goes up. Regarding mass, if you melt our land-based ice in ice caps, ice sheets and glaciers, transferred into ocean basins and sea levels go up. But sea levels will differ from the global mean depending upon their regional or local processes. At the regional scale, we must understand processes such as the static equilibrium, the gravitational influence of our large land-based ice sheets. We must understand atmosphere-ocean dynamics, changes in the steric component to do with land level change. We must understand glacio-isostatic adjustment or vertical land motion both during and between earthquakes. On the local scale, we must try to get an understanding of sediment compaction, influences significantly our deltas on our planet, and also groundwater withdrawal, water that's extracted from our aquifers for industrial, commercial, or agricultural use, lowers the land surface and amplifies sea level effect. Each one of these processes varies in time, and in the annual reviews paper, we tried to illustrate this. So we have our processes, be they global, local, or regional. We have the time that they have a discernible influence on sea level, and then our shading indicates their potential magnitudes. So on the far left-hand side, if we look at ocean dynamics changes in sea surface heights to do with atmosphere-ocean interactions, has a duration of anywhere from seconds to decades to perhaps centuries, and a potential magnitude from centimeters to several meters. On the right-hand side of the diagram, at the other end of the temporal spectrum, we have dynamic topography. Dynamic topography changes in the Earth's topography as a result of mantle convection, has a discernible influence on tens to hundreds to millions, hundreds of thousands to millions of years, and its potential magnitudes from centimeters, several meters, and perhaps beyond. Many of these processes have a spatial fingerprint, which is shown on this slide for 4 of the processes which our group investigates. So we can look at dynamic sea levels. This is a fingerprint, a spatial fingerprint of one of the models that project under a high emission future out to 2100. This graphic here is the current influence of GIA projected by one of Dick Peltier's models. And in the bottom 2 panels, we show static equilibrium fingerprint if we have melting from Greenland or Antarctica. Now, in my career, as Adam said, when I moved to Durham University to do my PhD and then my subsequent postdoc work, I spent a lot of my time collecting data to constrain the process of glacio-isostatic adjustment, because in the UK, it had the British ice sheet, which meant the areas in Scotland were depressed at the last glacial maximum and then subsequently uplifted. We also collected data from the east or the south coast of the United Kingdom, which was located at the forebulge at the last glacial maximum and has subsequently been subsiding. When I went to the US, I spent much of my career looking at collecting data along the US Atlantic seaboard to constrain GIA, because the contribution of GIA substance in the United States is quite significant at rates of 2 to 3 millimeters per year. Now, this is a process that's quite complex to try and to explain to agencies. So I remember one of the presentations I gave was to the US military, and I showed how glacial ice static adjustment was the reason why you had much of the spatial variability in tide gauges. And I remember at that meeting, so I'm just going to show you, is that the commanding general stuck a medal on my chest afterwards for illuminating him on this process of GIA. And the medal is in that little, on the top shelf there. So that's one process that we spent a lot of time in the US looking at. The other process that we concern ourselves by looking at past sea level changes is the static equilibrium. So these ice sheets were of a colossal mass, water is attracted to it. When those ice sheets lose mass, the gravitational attraction is decreased, and you get the greatest sea level being felt in the far field. So these two images are if you have a melting of Greenland, a 1 meter contribution to global mean sea level from Greenland. This is the spatial fingerprint. In areas around the Arctic Circle, you would get a net sea level fall, with the greatest influences in the Southern Ocean or Singapore, for example. A 1 meter contribution from Greenland causes a 1.2 or so meter rise in sea level around Singapore. And this is one of the reasons why I got involved with the Singapore government, represented the Singapore government on its Arctic Council. It has an observer status, and I gave some presentations of how melting in the Arctic influences the coastlines there, but also significantly influences Singapore. Another problem or complexity is that our recorders of sea level have a differing time length of their observations and also have differing levels of precision. So we can have satellite-based imagery, provide very, very precise reconstructions of sea level, but they only go back to around the 1990s. We have tide gauge records, and tide gauge records set up by mariners cause the high and low tide. Those recorders can be averaged to give the average sea level of the day, and then you can have a time series. But if we want to look at a global distribution, we only really have these tide gauges from the 1950s. Yes, we do have some long-term tide gauges, but they're located in northwestern Europe. The Amsterdam tide gauge, for example, goes back to the 1700s. So if we want to look at processes that vary through time, for example, if we want to look at the climate-sea level relationship under periods that are not just an increase in temperature, we're going to have to start to use proxies. So I've spent much of my career looking at salt marshes in the temperate latitudes. We work with people who collect archaeological data, but we also work with microatolls. And Aaron Meltzner here at EOS is perhaps the #1 scientist in the world, not only in Western Singapore, to study microatolls. And they have a resolution of maybe plus or minus 10, 20 centimeters. We can go back further in time, but we lose our resolution. Sedimentary, coral reefs, or oxygen isotopes can take you back through previous interglacials. So let's start looking at some data now. So the time period that I've looked at is predominantly the Holocene, the last 11 or 12,000 years ago. And this is a statement from a sort of a review of sea level science that was done by Andrea Dutton, a MacArthur Fellow, in 2015. And in this paper, Andrea said that the Holocene has the most abundant and highly resolved relative reconstructions compared to previous interglacials, such as the last interglacial or the Pliocene. In addition, the history of the ice sheet retreat is relatively well constrained, particularly in the Northern Hemisphere. So that's the demise of the Laurentide and the Fenno-Scandinavian ice sheet. So we have this statement, but however, we have a conundrum or a problem that we don't know what global mean sea level was during this time period. So In the IPCC, we were faced with a problem. So the IPCC wants to have some cross-chapter time horizons for climate variables. So it wants each chapter to have information on the Pliocene, the last interglacial, the last glacial maximum, the mid-Holocene, pre-industrial, and then time periods in the 20th and the 21st century. So when it came to the Holocene, we were posed with this question: can we state what global mean sea level during the mid-Holocene, 6,000 years ago, was within half a meter, 1 meter, 2 meters, 5 meters of pre-industrial? So when this question was posed, if you look at what the IPCC is supposed to look at, a consensus of the literature, the data just simply wasn't there. On the graphic are the global mean sea level parts of a GIA model, be it the Kurt Lambeck group from ANU, Peltier's group, Toronto, or Sarah Bradley's, Glenn Mills, Jerry Metrovica's Harvard European collaboration. And the differences in their global mean sea level is quite significant. At the beginning of the Holocene, we have differences in somewhere in the order of 15 meters. When we get through to the mid-Holocene, we have differences of 5 to 7 meters, and they're quite profound in their both magnitude, but also their form. So Dick Peltier's model suggests that there has been zero global mean sea level in the last 6,000 years, and that means our current ice sheets, Greenland and Antarctica, have had no mass change, or that their mass change has balanced each other out. Conversely, Kurt Lambeck or Sarah Bradley have 5 to 7 meters contribution from Greenland and Antarctica. And that's a significant contribution with very minimal temperature forcing. So understanding global mean sea level in the Holocene is crucial for understanding the stability of our ice sheets when we move through into the latter parts of the 21st century and beyond. So how are we trying to resolve this? Well, we're trying to standardize all sea level measurements in the Holocene. And that means that you can compare a measurement in northern Russia, a sea level record in northern Russia, from a record in the Caribbean, from a record in South America. And all the areas here have been published by, and we culminated this in a QSR special issue. It was led by Nicole Kahn. She was a former postdoc here at EOS. She's now an assistant professor in Hong Kong. And in the dashed areas are areas that our group is currently working on now. They're part of Fang Yi's and Christabel's and also Stefan's work. So how do we standardize sea level? Well, what we need to do is we need to look at our sea level indicators, and we need to define their elevational relationship to the tidal frame, a relationship known as the indicative meaning. So this is a schematic of an intertidal zone in a temperate salt marsh, and you would have 4 sea level indicators. We would have uplands, which exist above high tide, subtidal communities existing below mean tide level, and then we have 2 salt marsh communities, a high marsh and a low marsh. So what we would do is we would go out into the modern intertidal zone and we'd survey the upper and lower elevational limits, and that is known as the indicative range, with the midpoint being the reference water level. So hypothetically, in this schematic, a low marsh is existing somewhere between mean high water and mean tide level. So how do we reconstruct sea level? Well, we'll take cores, we'll look at outcrops or bank sections, we'll know our depth below the ground surface, we'll survey that surface elevation to an elevation with respect to the tidal frame. We will then hypothetically take out these 4 sea level indicators that are datable, and they'll produce 3 different types of sea level data points. We can have freshwater limiting points, sea level is below, marine limiting points, sea level is above, and 2 different types of sea level index points. They identify where sea level was in time and in space with an associated uncertainty, both temporally and vertical. So let's look at an example. So this example is from Stefan Schwab. We've got a paper just ready to be submitted, which would provide a new sea level curve for Singapore. So Stefan, in his PhD, which was supervised by Adam, took a variety of long sedimentary cores, and working with our group, we've taken one of these cores and produced some new sea level data in Marina South. We then compared it with other published data around Singapore, standardized it so we could build up a sea level curve for Singapore. We then could look at other published or unpublished data on the west and east coast of the Peninsula Malaysia. And this diagram shows a map of the spatial fingerprint of glacial-isostatic adjustment at 6,000 years before present. So this is one of Stefan's cores. It's in this section of the core, it stretches down around 19 meters below present day mean sea level. It has a stratigraphy of sandy silt at the top of the core, and then it moves into mud material, and then at the base of the core we have an organic. We look at the pollen assemblages in the organic. This identifies that the organic is a mangrove. Therefore, we can define its indicative meaning and produce a series of index points. Overlying this in the mud and the sand material, where we have foraminifera, we can define those as marine limiting points. The chronology is quite superb, stretching back to 9,500 years ago and beautifully in stratigraphic order. So in the top panel here is the new sea level record for Singapore. Stefan's work is in light blue, the standardized other data is in purple. We're stretching back around 10,000 years now for Singapore and showing sea level rising in the early Holocene at a fast rate of rise from around -22 meters below present to a high stand of somewhere in around 4.5 meters at 6,000 years before present. We have a fast rate of rise, but the data that we have is unable to discern any stepped change or oscillation at the 8.2 climate event. When we compare it with the GIA model, here we're using one of the latest iterations of Dick Peltier, his I6G model. We show a significant difference in the early Holocene, some 10 to 15 meters. When we look at the high stand, yes, it's of a similar magnitude, but the timing is earlier in the GIA models. And when we look at the late Holocene sea level fall, yes, we don't have much data, but we do indicate that sea levels may have been below present in Singapore 1 to 2,000 years ago, which isn't discernible in the GIA model. So Stefan produced a database of sea level for Southeast Asia. I worked with Nicole to combine this record with data from Australia, with data from the Gulf of Mexico and data in the Caribbean. And then we had a tropical sea level database. And we used that database in a publication this summer to look at thresholds of mangrove survival. So sea level data can be used to constrain GIA models, as I've shown. It can be used to constrain climate models, but it also shows the evolution of environments in time with respect to sea level. So Nicole and I put together the data. Other co-author on this paper, notable co-author is Erica Ash. She was a graduate student of mine. She's a statistician. And then we worked with Neil Santaland's group, and we got the paper published in Science this summer. So why was science interested? Well, our mangroves and our coastal salt marshes are incredibly important ecosystems for carbon storage, for buffers to coastal erosion, for filtration of drinking water, for biodiversity hotspots. But there's a problem with the empirical data, which leads to a lot of uncertainty. So we can have a paper published in Nature showing that, or suggesting that the current empirical data shows that nearly 70% of our mangroves are already submerging. Then a paper comes out a year later saying, no, 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 it's not 70%. In actual fact, if you reanalyze the data, it's only 5% of our marshes and wetlands are submerging. Indeed, you can go into local studies that say on a regional basis, our mangroves and marshes aren't retreating and being lost, they're actually expanding. With this uncertainty in the data, it's not surprising that the models have great problems accurately predicting the future. You can have certain projections that say within the 21st century, 90% of our marshes and mangroves will be lost. Other papers showing less than 50%. The other reason the paper was published in Science was because it's a new type of data to look at this problem. So when we produce our sea level databases, not only do we produce data on how sea levels changed, the way the databases are set up is that we put in their stratigraphical context. We describe the sediments both beneath and above the dated contact. We also assign each one of those dates a sea level tendency, which describes whether we have a positive or a negative sea level tendency, positive, an increase in marine influence, a negative, a decrease in marine influence. So if we had an organic deposit that across the dated contact was overlain by a clastic deposit, where we have a sea level indicator that shows an increase in marine influence, so a change from a brackish to a marine deposit, we would describe this as a positive sea level tendency, an increase in marine influence, and we would infer in a tropical setting that this is a change from a mangrove to a mudflat deposit, recording marsh retreat, mangrove retreat, or mangrove submergence. Conversely, if across the dated contact we had a clastic deposit overlain by an organic deposit, our sea level indicators showed a decrease in marine influence from marine to brackish material, we would assign this regressive contact a negative sea level tendency. It would be a replacement of a mudflat from to a mangrove deposit. It would evoke the initiation of mangrove vertical accretion, and when we have many dates within the stratigraphic column, we could say that the mangrove is keeping pace with sea level. So in this paper, we had 80 different geographical locations within the tropics. And when we analyzed this data, we could subdivide it into two geographical regions regarding when mangroves started to initiate. In panel A is the initiation of the mangroves between 10 and 6,500 years ago. In panel B, which has a different spatial distribution, the mangroves initiated 6,500 years ago. We could evoke two different models of coastal evolution. In regions A, now these are true far-field regions, they have no influence from glacial-isostatic subsidence. So we suggested that in phase one, sea level rates would have lowered sufficiently for mangrove development. And this would continue up to a mid-Holocene high stand. From the mid-Holocene high stand to present, we'd get delta progradation. And this form of sea level curve in this schematic is shown for Queensland, Australia, but we just showed you an example for Singapore. In the other region, we would have fast rates of sea level rise in the early Holocene, and these are faster than in region A because these are regions that are still influenced by glacial isostatic subsidence, regions in the Gulf of Mexico and the Caribbean. And therefore, mangrove initiation did not begin until much later, to around 6,500 years ago. For those two regions, we then could look through the database, we could calculate the rates of sea level change and compare them with rates of marsh accretion. And from these diagrams, you can see a correspondence between how, if relative sea level drops, marsh initiation starts and then is in parallel. Erica Ash was then able to develop a statistical model that could look at the probability of marsh initiation for different rates of sea level change. And this table comes from the paper. And what we're showing in this table is what the 90% probability is of marshes or mangrove initiation under different rates of sea level change. So globally, we're suggesting that sea level rates need to be 6.1 millimeters or below for mangrove accretion to continue. And then you can subdivide it between the regions, 5 or 7 millimeters. So we have a range, we have their uncertainties here, but we have a range of between 5 and 7 millimeters. Now that's quite interesting because there are a couple of other papers that also have this threshold of around 6-7 millimeters per year. So if we look, this was a paper that I wrote a couple of years ago looking at salt marshes in the United Kingdom. And I suggested that when Holocene sea level records or Holocene salt marsh records, the marshes are 9 times more likely to retreat than expand when relative sea level is greater than 7.1 millimeters per year. A colleague of mine, Tor Tornquist, showed that if rates get between 6 and 9 millimeters per year, the marshes in the Mississippi Delta will turn to open water within 50 years. So what about looking at future sea levels? Well, within my research group, we've never had really the capabilities to produce models that project the future. Yes, I've been involved in some semi-empirical models, but not the process-based models. But in my methodologies that I've tried to show previously, we've been all about standardizing measurements. So when I started to think about future projections of sea level, I started to think about, well, could we standardize future projections so we could compare one projection with the other, but in particular compare the projections with the IPCC reports. And this is what we did in an Earth's Future paper. It was led by Andrew Garner, who was my postdoc for several years. So this graphic here shows time of publication along the x-axis. The diameter of the circles, or the number within the circle, shows the number of publications that project sea level in particular year. And the y-axis shows the sum of the number of different types of projections. So the first projection of sea level was by Vivian Gornitz, a scientist from NASA Goddard in New York City. She produced her projection out to 2050 and did a doubling of CO2. Conversely, if we go through to 2017, there were 11 publications projecting sea level, and they had 50 or so projections, because nowadays when a paper is written on projections, you look at a variety of RCPs, which are emission scenarios. We can look at Paris agreements. We look at 1 degree C, 2 degrees C, 3 degrees C worlds. So there's been a change in the number of publications. In the 80s and 90s, I would say that these are the time horizons of the IPCC. I would say the jobs of the first, second, or third assessment reports were relatively easy. They only had a few papers to deal with to describe the consensus of scientific opinion at that time. The fourth assessment report had a problem, because there were no publications for which to derive their assessment. So the IPCC themselves in the fourth assessment came up with their own modeling structure to develop projections. And this, as well as the societal importance of sea level, catalyzed a lot of other publications. So by the time of the IPCC 5AR, there are 20 or so publications. And now we're dealing with the sixth assessment, there are far greater than 20 publications. The next thing I wanted to do is, because I'd started to standardize them, I could compare projections between them others, and I could also compare them with the IPCC. So Andrew put together this really interesting figure. So in this figure, we've got time along the x-axis. We've got the projection of sea level rise, and this is the projection for a high emission future out to 2100. What's the upper limit of the individual publications? And we have symbols depending upon the methodology used. So we could have expert judgments. I'm going to show you one of them in a minute. They can be literature synthesis or a variety of different models. We also have the IPCC ranges for the upper emission scenario. And you can quite clearly see that each one of those individual projections is greater or equal to the IPCC ranges. So you can conclude from this that the IPCC is a conservative body, that it errs on the least side of drama. So I wanted to investigate this a little bit further, that why is there this difference between the individual studies and the IPCC? To do this, I did an expert elicitation of sea level rise. So this was a paper that came out this summer. It's from members of my current and past research group. Janice helped out significantly in developing the survey that we gave to the experts. Neve Cahill did the statistics regarding of this, and we added some academic stardust through Stefan Ramsdorf. So we did an expert elicitation. So the expert elicitation, we identified sea level experts. We defined this through looking through the Web of Science. We went through the Web of Science and identified experts that had published 6 or more papers in the previous 5 years on the topic of sea level. We had 106 experts respond to our survey. We asked those experts a variety of questions regarding sea level. We asked them what they thought their likely and very likely estimates were of sea level. So this is IPCC terminology. The likely range is between the 17th and the 83rd percentile. The very likely range is between the 5th and the 95th percentile. And we asked them what they thought sea level would be at 2100 under a low and a high emission scenario, and 2300 under a low and a high emission scenario. So we put together all the expert estimates. Neve was able to put these together as probability density functions, and they're displayed on this graph. Now, we repeated a survey that we did several years before. So I wrote a survey paper in 2014, and then we repeated it in 2020, and it used the same methodology, very, very similar questions, so we could directly compare the results. So in the top row, we show sea level rise at 2100, and in the bottom row, we show sea level rise at 2300. On the left-hand side is the low emission scenario, and on the right-hand side is the high emission scenario. If we look at the low emission scenario or the high emission scenario at 2100, there is no noticeable change between the survey in 2014 and the survey in 2020. If we look at the 95th percentile under the low emission future, it's somewhere between 80 centimeters and 90 centimeters. Under the high emission scenario, it's somewhere in the order of between 1.6 and 1.7 meters for the 95th percentile. But when we go out to 2300, there has been a significant change from the estimates in 2014 and 2020. We have a much longer tail, indicating much more uncertainty within the scientific community. Under the low emission, it goes from 2.6 to 3.1. But the estimates from the experts for 2300 are incredibly scary, from 4.9 meters to now a 95th percentile of 7.8 meters, estimated global mean sea level rise by 2100. To reinforce the statement that I showed earlier, we can compare the assessment in 2014 the assessment in 2020 with the IPCC's 5th assessment, and then an IPCC special report called SROC, it published in 2019. We can see a great deal of correspondence in the likely ranges, particularly at the low emission. But when we look at the estimates at the high emission scenario for 2100, AR4 has an upper likely estimate of 98 centimeters. 2019 is 1.1 meters. We have significantly higher than that. In the survey, we wanted to ask the experts, well, what were the reasons for this uncertainty, these large ranges that you're providing? And the great majority of sources of uncertainty are associated with the ice sheets, both at 2100 and 2300. And if you delved a bit deeper, it's the uncertainty of the Antarctic ice sheet. And then if you ask which were the processes that they are uncertain about, it's marine ice sheet instability and a new concept known as marine ice cliff instability. We then asked the experts, what were the publications that were most influential in coming up with your estimations? And these answers are also interesting in that the number one, both for their estimates at 2100 and 2300, is a paper by Rob DeConto and Dave Pollard published in 2016 in Nature. And these were more heavily used than the IPCC. Rob DeConto and Dave Pollard's paper use a process known as marine ice cliff instability to enable the model to fit paleo data from previous interglacials. And they state that later in this century and beyond, this process of marine cliff instability will influence the Antarctic ice sheet, which means that by 2100, this ice sheet alone will contribute 1 meter to global mean sea level. And it's interesting that this paper is more heavily cited than Tamsin Edwards or Nick Coolidge. Nick gave a presentation to the ASC and EOS community, and both of these papers said that marine cliff instability was not necessary to fit the paleo data, refuting some of the findings of DeConto and Pollard. So to bring this to a close, I hope I've been able to show you the sort of theme that our research group does for some of our publications. I began by looking at the annual reviews paper that we published as a group. I'm a big fan of publishing annual review papers when you come to a point in your science where you think you have enough information to pull together. In this, Bob and I also had an ulterior motive of trying to use it as a basis for providing the structure to an IPCC chapter. But I've published review papers before, particularly with graduate students. Graduate students can spend many, many months doing a literature search on a particular topic, and you can use, the students can use those processes to try and produce a paper. And when we're in a pandemic where we're not allowed to do fieldwork, this is one element that you can use. And I've had my graduate students publishing papers in Earth Science Reviews and QSR, etc. The second paper is all about the application of paleo data. So I've always been interested in fundamental science, and we can apply it to policy relevant problems. And I've always been fascinated by how ecologists manipulate the modern environment to be analogous for the future. Well, as geologists, we can look in the past and do we have analogies for what may happen in the future? And that's what we did with the Mangrove paper. The bottom two publications are about projections. And yes, you can be interested in fundamental science, but I've always been aware that you need to be a scientist that provides the information that agencies want or funding body wants. And here in Singapore, ever so concerned about sea level rise. So we got into the realms of sea level projections by Turning to the techniques, our group knew very well about standardization of measurements, or looking at the goodwill of the scientific community. So thank you very much for listening, and thank you again, Susanna and Adriana, for putting on this seminar series.